All right, in this lesson we're going to learn a new technique for integrating. It's not necessarily a rule like the power rule or your trigonometric rules, but it is a rule that helps to undo a situation that we learned when we were differentiating. This technique is called integration by substitution. We specifically use U substitution, which is something you perhaps are familiar with, and we want to use that to rewrite and evaluate definite and indefinite integrals on a derivative where the chain rule has been applied. So our goal today is to learn how to undo the chain rule. As you remember that there were some other more complicated rules that we learned, like the product and quotient rule, but we actually focus in on that in a different unit of study. Today we're looking at how to undo the chain rule. Okay, so we are going to use U substitution as a way to rewrite these integrals so they look like they're in a form that's easier for us to simplify. Just like back when we learned the original chain rule, our goal for today is to try to determine what the inside function is, and since we'll be looking at a derivative, we also want to identify the derivative of the inside. So let's warm up with how we applied the chain rule in the first place, because this will give us some good context for continuing. How did we take the derivative of something like f of x equals the cube root of 7x to the fourth minus 8x? Well, the first thing that we did was we probably did some kind of a rewrite, so 7x to the fourth minus 8x to the 1/3 power. So my inside was 7x to the fourth minus 8x. The outside was to the 1/3. I usually call this a something to the 1/3 issue. So when I go ahead and I take the derivative, I bring down the power of 1/3, and then I'm going to have the inside, which stays the same, to the power of negative 2/3, because recall that you go down a power, times the derivative of the inside, which would be 28x cubed minus 8. So when we're working backwards today, we want to try to identify, well, what was that inside? Can I see its derivative somewhere in the problem and rewrite it in such a way that it similar to what we did when we took derivatives. So I'll show you an example of what I mean on the next slide. So if I have the integral of x squared plus 1 quantity squared times 2x dx. So what are the inside and what are the derivative of the inside? So when I look at this, and I'm a little more practiced, I see something being squared. Okay, so let's try to say, let's try to see if that's our inside. Is the inside x squared plus 1? Well, if I'm going to let that equal u, I would want to make sure that its derivative is somewhere in the problem if a chain rule has been applied. What's the derivative of x squared plus 1? Well, that's 2x dx, which conveniently I have. So what we want to do next is, now that I've accounted for all the parts, is I want to do a rewrite. So I'm going to say what I really have now is u squared du. Every piece that's here must be accounted for and be equivalent to what's there. This is an expression. I'm not allowed to do any operations. It must remain exactly the same. Okay? This problem is something that I can very easily integrate. The u would go up to the 3rd power. I'd have a 1/3 out front, and then this is an indefinite integral, so I need a plus c. Please be careful to make sure that you switch back to x's. The original problem was in terms of x. So 1/3 times quantity x squared plus 1 cubed plus c. Okay, that's how U substitution works. I think there will be some cases where the U and the du will be more obvious than others, so let's just try to expand and look at a bunch of different options here. Okay, so what if I have the integral of 5 cosine 5x dx? Often when you worked with trig functions, the inside of the trig function, if it was something other than x, was your inside. So my u is 5x. The derivative of 5x is 5 dx, and I have a 5 and a dx. So then everything's been accounted for. So this is really a cosine u du. The antiderivative of cosine is positive sine. So sine of 5x plus c. And I want to give you the quick reminder that if you're not sure if you're doing this right, if you take the derivative of your answer, it should match up with this. The derivative of sine of 5x would be cosine of 5x times 5 by chain rule. Okay, so let's go ahead and take a look at here. So this is actually very similar to that previous example that we had looked at. I see x squared plus 1 being squared, so to me this seems like it should be the inside. So let's explore that idea. The derivative of that would be 2x dx. Well, that's very close to what I have. I have an x and a dx. Unfortunately, very close is not good enough. If I say that this is my u and this is my du, I've created an extra 2 that's not in the actual integral. So I can, if I create an extra constant, I can actually balance that out by multiplying by a 1/2. So if I multiply by a 1/2, I can say I have a u squared du. My du had an extra 2 that wasn't there, so I had to balance that by having a 1/2 out front. So anytime you create an extra constant, when you take the derivative of your inside that isn't in the formula, you do need to balance that out by having that reciprocal of that out front. All right, so then u is going to go up to u cubed. I'm going to have 1/2 times 1/3, which is 1/6. So 1/6 u stood for x squared plus 1, quantity cubed, plus c. It's very common that you'll have to compensate for a constant. All right, so let's keep going. All right, so I have the integral of square root of 2x minus 1 dx. So what's under the radical often was what was your inside when we did derivatives. So let's just keep going with that same intuitive feeling on that. So the derivative of this turns out to be 2. Okay, I have the dx, but unfortunately I don't have that extra 2. So I would need to compensate for that by having a 1/2 out front. U to the 1/2, or the square root of u, du. Okay, so I'm going to go up to u to the 3/2 power. Had a 1/2 hanging out, and then I'm going to have a 2/3. 2's cancel, so I'm left with 1/3 times 2x minus 1 to the 3/2 plus c. Okay, so just I want to pause and make a quick comment here. As you probably realized when we learned derivative rules, that once we learned the chain rule, you saw that the chain rule was used with many functions. There were very few circumstances where you were not actually applying chain rule, because most functions have some type of a composition with them. The same is going to be true with u substitution with integration. From here on out, you're going to find yourself using u substitution quite often. So don't be surprised if you feel like you're using it more often than not. Okay? So let's look at the next example. It looks much more complicated than it actually is. So we have the integral of sine squared of 3x times cosine of 3x dx. So what might be nice, even though this is considered standard notation, but to help you identify inside and outside functions, let's rewrite that just a bit differently. Because when you do that rewrite, you might see that if I were to make some kind of an educated guess, that looks like it would be the inside since it's a quantity being squared. So let's go ahead and go with that. If you pick wrong, then you just have to pick something else next time. So if u is equal to sine of 3x, the derivative of that would be cosine of 3x times 3 dx. Well, that's good because we have a cosine of 3x dx. However, we don't have this extra constant of 3, so I just need to compensate for that by having a 1/3 out front. So then this becomes a u squared du problem. So even though you might have thought that this looked like a really complicated trig problem, look how easy we were able to rewrite it into something that we can do quite quickly. So I'm going to go up to u cubed. The 1/3's hanging out from before, and I created a new 1/3 with the power rule. Okay, so I'm going to have a 1/9. U stood for sine of 3x cubed plus c. If you wanted to see what that looked like, with that other trig notation, remember that you can put the power right there. Like that. Okay. Well, so far we've looked at all indefinite integrals, and we need to talk about how you evaluate these as definite integrals. Not necessarily any big surprises here, but it is something that we do need to address. Okay. There are two different methods for evaluating definite integrals. They're both very important. You can choose your preference, but you do need to understand both because they both do show up on the AP exam. And it's just better for a deeper understanding of antiderivatives, which you'll study in depth in Calc 2. Okay, so let's just dig right in and see where we go. So on this one, I can see that I have something being cubed, so I would start with trying that as my inside function. The derivative of that is 2x dx. I have the x and the dx. I don't have the 2, so I'm going to have a 1/2 out here to compensate. And it is a u cubed problem. All right, so what I would like to do is illustrate the first method for how to evaluate definite integrals with u substitution. The first method recommends that once you've switched to u, that we've done, is that you switch everything to u and you no longer at any point ever go back to x. So this is actually the method that's most commonly used by people that study calculus, but I want to show you both methods. So what I mean by switch everything to u's is these bounds go with x variables, and if I want to switch everything to u variables, I need to switch the bounds as well. So if x is equal to 0, what's u equal to? U would equal 0 squared plus 2. Because u equals x squared plus 2. 0 squared plus 2 is 2. If I want to switch the upper bound, x is 1, right? Well, what is u equal to? 1 squared plus 2, which is 3. So now I've completely converted the problem from x variables to u variables, and at no other time in this process do I need to go back and switch back to x. So let me show you what I mean. So I'm going to go up to u to the 4th power. I'm going to have a 1/4 out front, so I'm going to have a 1/8, and my new bounds are just from 2 to 3. So I can go ahead and I plug in the upper bound, so times 3 to the 4th minus 2 to the 4th. And when I go ahead and I evaluate that, oh, this is a 1/8, pardon me. When I go back and evaluate that, I get 8 and 1/8, or 8.125. So notice I never went back to the variable x. You need to know how to do this change of variables. It is a required AP concept. I would also say it's critical for those of you to understand that are going to go on to Calc 2. Okay? An alternative method that some people prefer, like I said, it really doesn't matter, is once they've rewritten and they've said, okay, 1/2 u cubed du, notice that you wouldn't put the bounds back in, but you go ahead and you evaluate this problem. So then again, we get u to the 4th with a 1/8 out front. And then what you would need to do now is if you wanted to not switch your bounds to u bounds, is you would switch back to x. So 1/8 times x squared plus 2 to the 4th. And I would switch back to my x bounds of 0 and 1. So I'm going to have 1 squared plus 2 to the 4th minus 0 squared plus 2 to the 4th. And then if I have, that ends up simplifying to the same thing, the 8 and 1/8, or 8.125. Again, either method gets you the same result. Sometimes the problem's messier and maybe one method works better than the other, but it's to your advantage to understand how both methods work. There's not a large difference between the two. A lot of students right away just like to switch back to x, but you do need to be aware that you do need to know how to switch over to u's completely, that is a critical skill for this topic. All right, so then we have one last example to look at right here. I have the integral of x times the square root of 2x minus 1 dx. So then this would be a different type of a rewrite problem. So I guess out of all of these, this would be considered probably the most difficult scenario, but I hope that I can give you an example of this that'll help make it easier to understand. So u is 2x minus 1. Okay, so that's my inside. The derivative of that is 2 dx. All right, well, I have the dx. I don't have the 2, so I'm going to need a 1/2 out front for that. But unfortunately, I have an extra x hanging out. Well, just so that you're aware, you can't have anything like this. You can't have x's and u's both in the same problem. Since this is a variable, it needs to have the antiderivative taken, so you can't just bring it out front. That's not helpful. You're not allowed to do that because then you didn't actually take the antiderivative of x. So we need to be able to compensate for this and get everything back in terms of u. Okay, well, let's just see. We have an extra x hanging out. Is there a way to rewrite x in terms of u? Well, let's try to get x by itself here. So I end up adding the 1. And to get x by itself, I would then need to divide by 2. So this gives me a way to rewrite this integral up here, all in terms of u. So instead of an x, I'm going to substitute in a u plus 1 divided by 2 times the square root of u du. So this may appear to be worse than the original problem, but the original problem, you had no other rules to integrate it, and this is actually something you can evaluate once you clean it up a little bit. So I'll show you what I mean. So I'm going to take this divides by 2 out and make it a 1/4. Then I'm going to have a u plus 1 times u to the 1/2. Okay, so then just distribute. So u times u to the 1/2 is u to the 3/2. 1 times u to the 1/2 is u to the 1/2. Okay, so then this just becomes a simple power rule problem. I'm going to leave the 1/4 here hanging out. So if I have u to the 3/2, I'm going to go up to u to the 5/2 with the 2/5 out front. U to the 1/2 is going to go up to u to the 3/2 with the 2/3 hanging out front. Plus c. So I just get to go ahead and substitute in what u stands for. So 1/4 times 2/5 is 2/20 or 1/10. 2x minus 1 to the 5/2. 1/4 times 2/3 is 2/12 or 1/6 times 2x minus 1 to the 3/2 plus c. All right. So then this would be the most difficult case scenario. It's when you choose your inside function and you really only have one choice for that inside function, and you end up not being able to compensate for an extra variable in the problem. So what you do is you end up trying to rewrite that variable in terms of u, so you now have a new integral that can be rewritten all in terms of u that you can evaluate using alternative methods like just simplifying and using basic rules. All right, so in this lesson we talked about how we need to rewrite an integral, identifying the inside and its derivative to undo the chain rule. We looked at a variety of different rules, anywhere from polynomials or square roots to trigonometry, just to kind of give a good variety that should hopefully get you going on this topic.